All right, so in case we doubted that similar triangles are actually useful in geometry, we use them right away to prove two of the, what we might think of as the classical, almost ancient theorems in geometry, theorems of Pythagoras and of Apollonius, so both ancient Greeks. So the Pythagorean theorem, of course, is the famous theorem relating the lengths of the sides of a right triangle. So if the two sides adjacent to the right angle have lengths a and b, and the hypotenuse opposite the right angle has length c, then a squared plus b squared is equal to c squared. And the proof of this, there are many different proofs that have been discovered for this theorem. This one uses only what we know about similar triangles. So it takes the triangle ABC, where C is where our right angle is located, and it drops an altitude from C down to the segment from A to B. So in doing so, I'll label this right angle here. In doing so, we've gone from one right triangle to now a bunch of right triangles. Right? In fact, we have three different right triangles in our figure now that we've dropped this altitude: ABC, ADC, and BDC. And the lucky part for us is that because all three of those triangles share a right angle, we're already halfway to the AA criteria. All we have to do is justify that those triangles also share another angle. So for example, the angle at B is common to both ABC and CBD, and so combined with the right angle that they also share, we have the AA similarity criterion satisfied, which gives us this proportionality, that A is to Q as C is to A. Likewise, looking over at the angle at A, which is common to both ABC and to ADC, combined with the right angle that they also share, AA is satisfied for that pair of triangles as well, making those triangles similar and setting up the proportion of B to P being the same as C to B. And we've transformed this from a geometry problem now into an algebra problem, using the equiproportionality of the sides of these similar triangles. So from these two proportions, we can rearrange them just by taking the cross products to get on the one hand a squared, and there's where our a squared appears, is equal to CQ, and b squared, there's our b squared showing up, is equal to CP. All we need to do to get from there to the Pythagorean theorem is then to add those two equations together so we can discover our a squared plus b squared. But when we do that, the right-hand side is c times the quantity q plus p, and because by definition and by the collinearity of AD and B, p plus q gives us c. And hence c times the quantity q plus p is the same as c times c, giving us the Pythagorean theorem as a consequence. So this is, I think, a really neat proof of the Pythagorean theorem using what might be kind of a bare minimum of assumptions that we know about geometry. There are many other proofs that use things like area and other stuff like that, but we don't have area at our disposal in our foundations just yet. So we can do it just with the properties of similar triangles. So the Pythagorean theorem is really well known because right triangles are ubiquitous in geometry. We can find them in a lot of places. And so this is a theorem that then relates the lengths of the three sides of a right triangle together. Apollonius' theorem gives us a relationship between lengths in a triangle that's not necessarily a right triangle, but which we can prove using the Pythagorean theorem and discovering some right triangles in it. Apollonius' theorem can be used to find us a way of determining the length of a median in any triangle. So a median is just, again, a segment joining one vertex to the midpoint of the opposite side. So if in triangle ABC, I let M be the median on the side BC, M be the midpoint on the side BC, and then the median is the segment AM, then Apollonius' theorem is a Pythagorean-like theorem in the sense that if I call, let's say I call these sides here A and B, that's probably a poor choice of labels. Let's call them A and B. Then the left-hand side of Apollonius' theorem is a squared plus b squared. I'm taking some liberty with the order of that addition, but the left-hand side is a squared plus b squared. Now, if this were a right triangle, the right-hand side would be c squared because of Pythagoras, but that's not what we have here because that's not what we're shooting for. We don't have a right triangle yet, and what we're trying to shoot for is something that can tell us what the length of this median is. So that length of the median is right here, in AM. And Apollonius' theorem gives us that length, but it gives it to us in terms of this length here. So it includes both the length AM and the length BM. And the length BM is 1/2 the length of BC, again by construction because M is the midpoint. So how we prove this, the stroke of brilliance inherent in this proof, which is one of those things where in geometry probably whoever first proved this, I'm going to assume it was Apollonius or somebody related to Apollonius, probably tried a million things before they figured out that dropping an altitude from A to the other side is a way to get us started. Because as soon as I drop an altitude, I've gone from having no right triangles in my figure to suddenly having, gosh, 1, 2, 3. Is there 3 or is there more than 3? I don't know. There's at least 3 right triangles that we can play with now. And each one of those right triangles, we can use the Pythagorean theorem to tell us something about. So that begins by taking the left-hand side of Apollonius' theorem and trying to work towards the right. Classic algebra proof technique. I'm trying to prove that an equation is true, so I start with the left-hand side. And I'm going to try and replace quantities on the left-hand side with things that they are equal to and do enough algebra that makes me arrive at the right-hand side. And our replacements come in the form of the Pythagorean theorem. So AB squared, we observed, is nothing more than the square of the length of the hypotenuse of the right triangle ABD. So we start by applying the Pythagorean theorem to the right triangle ABD, which is what lets us replace AB squared, the square of the hypotenuse, with the sum of the squares of the legs, AD squared plus BD squared. Then we reach once again for the Pythagorean theorem, but this time to tell us about AC squared. So AC squared we can quantify because AC is the hypotenuse of a different right triangle. Namely, it's the hypotenuse of ADC. And the Pythagorean theorem applied to that right triangle makes the second replacement for us. So already we've applied the Pythagorean theorem twice, just to get from our first quantity over here to our second. Now is when we need to get a little bit creative. We do have a like term in both of these, in this expression. AD squared appears twice, so we can just consolidate it. Then we have to go looking for ways of replacing some of our quantities to get m in there somewhere. We haven't used m yet. So we do it in 2 different ways. First of all, as we've indicated here, by replacing BD, which is the length from this vertex of the triangle all the way to the foot of the altitude, replacing that with BM plus MD. Now that would seem to be an odd choice, were it not for the fact that we can also replace DC by the difference, BM minus MD, a fact which is not immediately obvious. In order to discover why that's true, we have to look at the other side of this triangle, the other part of the base BC, which goes from M to C. So M to C has 2 portions to it, the portion from M to D and the portion from D to C. Because D is collinear, and between M and C, we know that the sum MD plus DC equals MC. Right? The triangle inequality is an equality because our points are collinear. Arranging this to solve it for DC, we find that DC is the difference between MC and MD. It's that space between, right? Between the whole segment MC and the part which is just from M to D. And here is where we use the one fact that we otherwise have not used and will not otherwise use, and that is that M is the midpoint of the side BC. Because M is the midpoint, MC is the same thing as BM. So that's our crucial place where we've used something that we assumed. MC is equal to BM because M is the midpoint. And because that's true, DC is the difference, BM minus MD. And that's where the brilliance ends and the computation begins. Right? All we have to do now is the algebra necessary to expand out those squares. We're adding together a square of a sum with a square of a difference. And so we end up getting some nice cancellations going on in there, so that when the dust settles, what we have left with in this combination is just 2bm squared plus 2md squared, and then I have 2ad squared here at the end. And all that's necessary for us to get to the end of Apollonius' theorem is one more application of the Pythagorean theorem. This time applied to the right triangle AMD, the right triangle that connects A with the median with the foot of the altitude. So in that, the two perpendicular sides are MD and AD, and the hypotenuse is AM. And so that's Pythagorean theorem, getting us to the end, to our conclusion. So there would not be Apollonius' theorem without Pythagoras' theorem, probably. I think it would be difficult to separate the two of them. This one really heavily relies upon the Pythagorean theorem. But that's really all that it relies upon. There's not much else that we're using here. So as soon as we establish Pythagoras, we get Apollonius. Not obviously, but trivially, just through this sequence of manipulations.